Welcome back, everybody. Today we're going to be talking about interest and logistical growth. And we're really going to focus on logistic growth because we've talked enough about interest in other classes. Okay? So what is logistical growth? This is exponential. Final amount, the initial amount, and you're growing at some sort of rate over time. Okay? Its differential equation isn't based on time. It's based on population. So the more people you have, the more people you'll have next year, or next month, or tomorrow. It's not based on T, it's based on P, the population. Exponential graphs, well, let's talk about this. Real life population doesn't grow forever. You can't have more people and more people and more people, or I think in my examples I use fish or deer or squirrels. They can't grow forever. Eventually you're going to run out of space. So exponential is if it just can increase forever, like money or something like that that's not going to stop. Things that have a carrying capacity, some sort of limit, we use logistic growth. So here's an example of an exponential graph. You're used to it, it goes up like this, it goes up forever, and it never stops. And over a short amount of time, it makes sense for population to do that. This is an example of a logistic graph. It looks exponential for a while, but then it starts to level off. This K value at the top we call the carrying capacity. We use the letter M most of the time for this symbol. It's the maximum, okay? There's an asymptote up there that it can't get past. Here is the differential equation for logistic growth. And you need to know this. At least you need to have some idea of this. K is just the rate that it's growing. P is your present population, your initial population. 1 is 1. P again is your initial population. And M is the maximum population, called the carrying capacity. Okay? Again, notice, there's no T, there's no time in this. So you're not growing based on time, you're growing based on your population and the maximum population, the carrying capacity. So it's like exponential growth in that you don't have a maximum, you don't base it on time. Okay? If you want to solve this differential equation, you're going to get this. And we're going to do a problem with this. If you'd like me to prove it, come to class. It'll take multiple slides and I don't want you to have to watch it. M is the carrying capacity. B is some constant that you'll have to solve for. K is negative in this one. And it has to be negative because it's on the bottom of a fraction. And then T is time. So let's try a problem. A fishery releases 10 trout into a lake. After 5 years, there are 104 trout. It is believed that no more than 400 trout can be sustained in the lake. So let's write some things that we know. We know that the current population is 10. We know that time is 5. And we know that the maximum, the carrying capacity, is 4,000. So if I want to find P of T, P of T is M over 1 plus B e to the negative kt. We're going to find B first, and then we're going to use the information to find K. Well, how am I going to figure out B? Well, the original population was 10. The maximum is 4,000. We don't know what B is. E. I don't know what K is either, but if the initial population was 10, I'm not going to put 5 years in. If the initial population was 10, that's time equals 0. So what that means is that 10 has to equal 4,000 over 1 plus anything to the 0 power is 1, and it'll just give you B. Now you can solve for B. Here's pretty easy. Multiply this over, you'll get 10 times 1 plus B equals 4,000. Divide the 10 over, you'll get 1 plus B equals 400. And you'll get B equals 399. So I'm going to take that and plug it back into my problem. So now let's think about what I have. I have the population equals 4,000 over 1 plus 399 e to the negative kt. T is going to stay in the problem, but I still have k. I need to find k. Now I can go back and I can answer this part, or I can use this part. After 5 years, there are 104 trout in the lake. So now I have a time and a population. I can find K. So my population is 104. My time was 5. I can solve this problem. Let's multiply this over. So I'll get 104 plus 104 times 399 will be 41496 e to the negative 5k. And that's got to be equal to 4,000. By the way, you could very easily just put this into y1, put this into y2, and see where they cross. I'm doing a little bit more algebra than I need to here. Okay? I'm going to subtract the 100 over. So, and I'm going to divide the 41496 over. I'm going to do all this in one step. So that ends up being 3896 over 41496. I'm going to take the natural log of both sides, which will get rid of the e. This will become natural log of 3896 over 41496. That gets rid of the e, but I still have to get rid of the negative 5 with the k, so I'm going to multiply this side by negative 1/5, or I could have divided by negative 5. Now, to make life a little bit easier, we're going to go ahead and do this as a decimal. Usually we leave it as a big, ugly fraction, and you can, but the decimal is give or take 0.473. Now let's answer the first part of the problem. It says, what's the model? Well, we now know B and we know K. So the population model is 4,000 on top. 1 plus the B we found earlier was 399. E to the negative K T. Okay? So, what other questions can we answer that are from this problem? It says, write a differential equation that models this behavior. Well, the differential equation was Kp 1 minus P over M. Okay? I believe that's what it was earlier. Yep, 1 minus P over M. Just fill in what you have. Remember that the P is going to stay there because that's our variable. So dP over dt. The K we found earlier was 0.473. P 1 minus P over 4,000. So that's the answer to B. To find the answer to C, we need to use the equation we found earlier. C wants to know what will happen after 20 years. Well, that's not too bad. That's just P at 20. 4,000 over 1 plus 399 e to the negative 4.473 times 20 for T. You can type that into your calculator, and we're going to round to the nearest whole number because these are trout. So once you have the formula, C is very easy. So far we've found the formula, we have found the differential equation, and we've solved a very basic problem with it. Now let's do the hard one. When will the lake be full? Well, with logistic growth, theoretically you'll never hit 4,000. But in real life, the lake will get full to 4,000 at some point. What number, what population, what decimal, when you round it, will round to 4,000? The first number that you can get that will round to 4,000 is 3,999.5. Yes, I know you can't have 0.5 trout. What I mean is, once you get past 3,999, eventually you're going to get to 4,000. So mathematically, let's figure out when that happens. 4,000. 1 plus B was 399. E to the negative 0.473 T. You can solve this one by hand, but we're not going to. We're going to use our calculator and we're going to let you do this. Because I want to see what this logistical graph looks like. So let's go to y equals. Let's clear out our previous problems. 399.5. Alpha y equals 1 gives me a fraction. 4,000 on top. 1 plus 399 e to the negative 0.473x. So let's set up a window. We know time needs to start at 0. And let's take a guess. Let's try for 30 years. Population starts at 0. And we know it can't have more than 4,000. So let's go 4,100 just to make the graph fit. And let's take a look at the graph. Ooh. I think I made my y value too big. No, this is a great graph. You can see it. I didn't do 4,000, or 3,999.5. Sorry. Now let's look at the graph. So there's the full lake. Here's that logistical curve, that logistic graph. You can very clearly see that it's eventually going to get close to that maximum and just kind of flatten out. So second trace 5, enter, enter, enter. And it'll tell me there's no sign change. That's because I didn't zoom out far enough. So 30 is not a big enough window. Let's try 40. There's my maximum. Here comes the logistic curve again. It looks like it's going to cross, but it's so close we can't tell. Let's let it calculate it. And it does at 31.662 years. So we're going to do this one on the calculator. We're not going to do this by hand. And we're going to get a time of 31.662 years. That's when you're so close to 4,000 that you might as well round up to 4,000. Okay? Logistic graphs, all based off of this equation right here. Find the b and then use that to find the k. The differential equation here. And the rest of it is just solving.